Okay. We go to module 2 of chapter 3, continuing with high frequency behavior of electrical components. So, in this module we will handle capacitors, inductors and resistors under high frequencies, how they behave and what are the models we can make to reflect this behavior. Now, take any component. So, usually this component will have some lead which is in the form of a small round wire connected to the component. Then the moment you have conductors, we have seen in the previous module that it has some electric field around it, some anti-field around it. So, you can think of some parasitic capacitance and parasitic inductance associated with it. Parasitic means that like a parasite, it is not supposed to be there, but of course it is there in that sense. So, that it is kind of unwanted like a weed. So, we have some inductance and some capacitance, and that is, and some resistance also, because they are not ideal conductors. So, any lead will have a resistance, lead resistance, a lead inductance you will have, and a lead capacitance, a parallel element. So, these are the parasitic elements. Then after that you have your real idealized component. So, it can be a capacitor or an inductor, resistor, diode or a transistor, it can be anything. So, here we will consider the first three: capacitor, inductor and resistor. Then you may have some more parasitic elements depending upon the type of construction used in creating these components. So, we take the ideal capacitor. What is an ideal capacitor? Well, it has a symbol like this. So, this is the ideal capacitor, and it has a impedance which is a function of frequency. We know that it is 1 by j omega c, or in polar form we write 1 by omega c angle minus 90. It means that the impedance is voltage divided by current. So, voltage and current are 90 degrees phase shifted, and the current is leading the voltage by 90 degree. So, that is why you have this minus sign, or 1 by j, from that also you get a minus sign. You can look it in that way also. So, if you convert it into dB, you can immediately see that as the frequency is increasing, the impedance of an ideal capacitor is decreasing by 20 dB per decade. It means that for every 10 times increase in frequency, so if the frequency is increased 10 times, then impedance is decreased from the previous level by 20 dB. That is the meaning of minus 20 dB per decade. So, this is an ideal capacitor, and this is the angle minus 90 degree. Now, if you take a real capacitor, what are the other components we have to add to get the realistic model for the capacitor? So, we take a non-ideal capacitor. First of all, we take the lead parameters. You have a lead resistor also, but impedance of the capacitor is generally so high, you can most often neglect the lead resistor, which will be very small, or combine that into the resistor of the plate and windings of the capacitor. If it is a wound capacitor, we can absorb that into this. Then and similarly internally also you can have a inductance and the dielectric resistance of the capacitor across C, but that also is quite high. So, that also can be neglected. So, you can neglect some things in this because usually these capacitance have high values. So, finally, you end up with, and this capacitance can also be neglected or absorbed into the, because you are looking at a capacitance value which are generally high compared to the lead capacitance. So, you get as an approximate representation a series network of L, R and C. So, C is the idealized part of the capacitor, and R and L are mostly contributed by the leads or maybe even from the R mostly from the capacitance itself. So, this may be an idealized capacitor. So, it is a series resonance circuit. Sorry, this is not an idealized capacitor, this is a real capacitor as opposed to an idealized capacitor C. So, if we write the impedance of this real capacitor, then we get R plus j omega L plus 1 by j omega C. Now, you can do a baud plot, a frequency plot or BODE, baud plot of this. So, we are at the corners we are doing this idealization and we are assuming sharp turnaround at the corners just for easiness. So, let us take this impedance. You increase the impedance from 0 hertz, 0 frequency, and so then it is only R plus j omega L is 0. So, this part is 0 and this part is omega equal to 0 infinity idealized. So, you assume from some very high impedance, you are coming down from very high impedance for the capacitor for DC, because the DC is completely blocked by this capacitor. Then as the frequency is increased, this becomes a finite value, but since frequency is small, this is a high number compared to j omega L. This is still small and R is kind of constant. So, as the frequency continues to increase, you see that this impedance from the inductive part is increasing, whereas this impedance from the capacitive part is decreasing. So, inductive part increasing, capacitive part decreasing, and at some point both will become equal and cancel each other. So, because this is j omega L, this is 1 by j is minus j. So, these two can the sum of this value is decreasing all the time as the frequency is getting increased. So, finally, that impedance comes down. So, during this regime it is acting as a capacitor. So, at this frequency, when impedance of this part and this part are equal, total impedance become the resistance R. Then beyond that, this part is dominant, inductive part is dominant. So, then from that time onwards, you have approximately 20 dB per decade increase in impedance as you would expect from an inductor. Same thing will happens with the phase also, minus 90, here it transition into plus 90 as if it is an inductor. So, this transition frequency or resonance frequency is given by when these two are equal j omega L equals 1 by j omega c, and that is given by 1 by 2 pi square root of L c when these two terms are equal. So, that is the resonant frequency. So, above the resonant frequency, the idealized capacitor is not really acting as a capacitor, it is acting more like an inductor. So, while selecting a capacitor, you have to know what is the resonance frequency of that capacitor, and you have to know the operating frequency where the capacitor will be employed, and the operating frequency should be much less than the resonance frequency. You can't use it at any frequency. And then how do you reduce or how do you increase the resonant frequency? If you make the leads of the capacitor as small as possible, you can do so. That is shown in this view graph. It's the influence of component lead. So, here a short lead capacitor, same capacitor, in one before soldering the leads are cut off and only 2 millimeter is retained. In the other you keep a long lead 12 millimeter. Then you compare the impedance as a function of frequency. Then you can see that with the short lead, the resonance frequency in this particular case may be at around 120 megahertz, and at that time it may have a resistance of 0.1 ohms. So, you can operate easily at 100 megahertz without any problem. It will be like a capacitive element. Whereas, another person taking the same component for the same application may have a long lead, and then the resonant frequency of that will be, because parasitic inductance is now larger, resistance is also larger. So, it is at 70 megahertz and resistance is 0.15. So, if you try to operate it at 100 megahertz, it will not succeed because it is not behaving as a capacitor, more like an inductor it is behaving. So, the circuit will not work properly. One is the self resonance frequency of the capacitor. The operation should be below that frequency. Then, since capacitor is kind of a high impedance element, and along with the leads, it can act as a pickup antenna for high frequency ambient noise. So, that one has to be aware. And there can be ringing due to resonance with cable inductance if a cable is used in connecting this capacitor. Then it works best in high impedance circuits. Suppose you want to reduce the noise in a circuit, everyone knows that capacitor is more like a bypass element, because at a high frequency it shorts out high frequencies. So, it is an ideal thing to use at the input terminus of the equipment you want to protect or the circuit you want to protect. But if your circuit is already of low impedance, it may not work very well, because your capacitance impedance under noise condition has to be even lower than the circuit impedance to be effective, and that will be at really high frequencies. So, capacitance as a noise filter works best with other high impedance circuits, not with low impedance circuits. Now, inductors. This is the representation of an ideal inductor. Impedance is j omega L, omega is the frequency, and angle 90 degree, the phase difference between voltage and current. So the current is lagging behind the voltage by 90 degree. So 20 log Z equal to 20 log 2 pi L plus 20 log F. So you see that it is 20 dB per decade increase in impedance as the frequency 10 times increase in frequency, then 20 dB increase in impedance. This part is constant and 90 degree. So this is the ideal inductor. So we again model this ideal inductor. You have a lead, you can have some resistance, then inductor and capacitance. Then you can have from the inductance winding you can have some resistance also, and a parasitic capacitance across the inductor turns if it is wound inductor, or across the terminals internal terminals of the inductor. So many of these things can be combined together, and you can, so basically essentially you have an L and R in parallel with a capacitance C. So this is the minimum high frequency model of an inductor. Depending upon the applications, one can have even more complicated models, but usually this would be sufficient. Now let us see how it will behave as the frequency is increased in the form of a Bott plot. So this is the real inductor. Impedance is R plus j omega L of this branch in parallel with the capacitive branch, in parallel with 1 by j omega c. So you can write out the expression for inductance. But what we are expression for the impedance. What we are mostly interested is how the impedance varies with the frequency. So again, following the same exercise from almost very small values, when omega is extremely small, this is small. So this is in parallel with this one. So this is a high impedance. So this is mostly dominant one. So this parallel branch is not very dominant. It's almost like an open circuit. So initially it is R, then it is j omega L that is dominating. Then at one particular point, j omega L and 1 by j omega c become equal. So that is this resonant frequency. So now this is high at this parallel resonance. So it is high impedance at resonance. Whereas previously in series impedance it is in series resonance it is low impedance at resonance frequency. So after that, after resonance, the capacitance part is dominant and 20 dB per decade decrease. So corresponding phase angle. So this is an ideal inductor. So you can operate the inductor in this frequency band below this resonance frequency. So inductors are also used as a noise filter. So here what are the factors to consider? One is the self-resonance frequency of the inductor, and inductor is most effective in the low impedance circuits because inductors are connected in parallel. So as the frequency is increasing, inductor impedance is also increasing, and it should be much higher than your normal impedance, and it is easy to be higher than the normal impedance of the circuit if your circuit already is having a low impedance. So this is most effective in the low impedance circuits. The possibility of ringing due to resonance with parasitic capacitance is another factor to be considered. And in inductors with ferromagnetic cores, the nonlinear effect of saturation must be considered. So this is a ferromagnetic core. So mu is defined as changes in flux density to magnetic flux intensity. So this is the saturation region. So one should not operate in the saturation region. It has to be somewhere here. So these are the factors to be considered while selecting inductance as a noise filter. And often we use chokes and ferrites in electronic components. So if you connect a monitor, sometimes you can find a round heavy thing on the cable itself, and that is a high frequency choke. This is for filtering out the noises coming from the supply, or for preventing the noises going from your device to the power lines. So these are the differential mode currents. So with the normal winding, the fluxes are opposing to each other. So it is a very low impedance, because the total flux is almost 0. So you have a low impedance differential mode impedance per winding. Now this is a single primary, this is several turns. Now for common mode type of currents, where the current directions are the same in both fluxes aid each other, and you have then high impedance per winding under common mode noise currents. So then it will kind of introduce a high impedance in the circuit, and you block the noise. Now modeling a real resistor for high frequencies. Again, we do the same exercise of including the parasitic elements of the component leads, the inductor and capacitor. There can be a leakage capacitance across the resistor also, which we can combine with this parasitic element. So you get a circuit in which you have an inductor, then you have a capacitor and resistor connected in parallel. So this will be the minimum model for a real resistor under high frequency. Consider a real resistance R. It has got, due to the leads and due to the construction of the resistor, some parasitic inductance L and some parasitic capacitance C. Now as the frequency is increasing, or at DC value, the parasitic capacitive impedance is very high, and the parasitic capacitive impedance reduces as the frequency is increasing, and at the same time the parasitic inductive impedance is increasing as the frequency is increasing. Now as you move away from the DC value, you can see that at one point resistance R become equal to 1 by j omega C, and that point is given by this. So the capacitive impedance is coming from very high value, so they are in parallel combination. So at this point both of them become equals, R equal to 1 by omega C. So that frequency corresponds to 1 by 2 pi RC. Beyond that it becomes capacitive. So the resistance remain as resistive only below this particular frequency of 1 by 2 pi RC. After that it becomes capacitive. Then inductive impedance is also increasing, and capacitive impedance is decreasing, and at some point of frequency both become equal and you have a resonance, and that resonance point is given by here 1 by 2 pi root LC. And beyond that resonance point, inductive impedance is much more than capacitive impedance. So it behaves as a inductor. So all these three phases you can find it over here. The resistive phase, so this is where the resistor should operate. Then after that you can have a capacitive and inductive phase also. So resistor is not supposed to operate in this area. Only below this frequency it is supposed to operate. We will see in the next slide another case also where you don't have this capacitive phase, in which resistance directly go from resistive to inductive phase. This happens mainly with low value resistors. That we will see in the next slide. Resistors, real value of resistors. Let us consider another possibility with very low value resistors. Now that possibility comes when your R, the inductance impedance first become equal to R, and capacitive impedance still becomes, that is the parallel branch, that becomes still very large. So what happens in that case? So this is still very large, so this is negligible. You have only L and R in the circuit. So in that case, at this frequency, when R equal to 1 by 2 pi f, R is equal to 2 pi f L, then beyond that, beyond this frequency, you have inductive 20 dB per decade increase, inductive increase. So from resistive to inductive it is going directly without going through the capacitive phase. So you have resistance and you have inductance, the phase angle. So this is another possibility with very value resistors. So we often say that if you are selecting for an applications very low value resistors, you have to be extremely careful about parasitic inductance, parasitic inductance, not really parasitic capacitance. That is where you have the main problem will happen, because this will be the Bott plot corresponding to it. From low value of resistor, immediately you go into the inductive part of it. Whereas if you have very high value resistors, say thousands of ohms, then parasitic capacitance becomes more problematic. So then the Bott plot will be something like this. From resistance to capacitive it will go into. So depending upon the application area, depending upon the low value or high value of the resistor, one of these two Bott plot will be more appropriate to be applied. So two different models are possible for resistor. Factors to consider in the use of resistors. One is parasitic capacitance is the main problem for high value resistors. Parasitic inductance is the main problem for low value resistors. To avoid these problems, shorten the leads as much as possible. Then you reduce the parasitic elements, both parasitic inductance, parasitic resistance and parasitic capacitance. Connect many smaller value resistors in series to get a high value resistance value. So suppose you need to have a high resistance value. So instead of using say 20 mega ohm or 1 mega ohm resistor directly, you can take 10 say 100 kilohertz 100 kilo ohm resistors and connect them in series. So then parasitic capacitance values are coming in series. So effectively you are reducing it. Now, if you want a low value resistor, you can take slightly higher value resistors and connect them parallelly, because then you are parallelly connecting all the parasitic inductance, effectively reducing the inductance problem. So, these are the two techniques you can use in circumventing the effect of parasitic elements. So, that is the end of module 2.